everyone, in this class also I wish to discuss about the numericals based on the photoelectric effect. So see the problem here. When electromagnetic radiation wavelength 300 nanometer falls on the surface of the sodium, then the electron are emitted with a kinetic energy of 1.68 into 10 raised to 5 joule per mole. What is the minimum energy needed to remove an electron from the sodium? What is the maximum wavelength that will cause a photoelectron to be emitted? So see here what the given data they give us and what they asked to find us. So when electromagnetic radiation of a wavelength falls on the surface of the sodium, so they give us the wavelength. They told us 300 nanometer wavelength of a light falls on the surface of the sodium. Then what happened? The electron are emitted with a kinetic energy of 1.68 into 10 raised to 5 joule per mole. They give us only the kinetic energy of the electron. They give us only the kinetic energy of the electron, that is how much? 1.68 into 10 raised to 5 joule per mole. Then what is the minimum energy needed to remove an electron? So they don't give us. So how much energy needed to eject the electron or the minimum energy needed to remove an electron from the sodium? We don't know that. Total energy is equals to question mark. Then what is the maximum wavelength of will cause a photoelectron to be emitted? I already told you in a previous class, at a certain frequency or at a certain wavelength, when the incident radiation having the certain frequency or certain wavelength, then only we have seen the photoelectric effect. So they asked to us the maximum wavelength that will cause the photoelectron to be emitted. So they asked maximum wavelength. Maximum wavelength. Here we have to calculate in a first step, that is the energy of or the total energy of a one photon. That's why you already know that E is equals to h mu equation. But we don't have a frequency. They give us a 300 nanometer light falls on the sodium. Then what we have to do here? E is equals to hc by lambda. We have to use this formula. So by using this formula, we find the total energy of a one photon. So see here, h means the Planck's constant. The value is 6.626 into 10 raised to minus 34 joules second. Into c is speed of light, 3 into 10 raised to 8 meter per second, divided by, so lambda, what they are given to us, 300 nanometer. Nano means 10 raised to minus 9 meter. Then the 300 into 10 raised to minus 9 meter. Then by simplifying this answer, what we get here, 6.626 into 10 raised to minus 19. 10 raised to minus 19 joule. 10 raised to minus 19 joule. So next one, this is the total energy of one photon. But observe here, they give us the kinetic energy per mole. They give us the kinetic energy 1.68 into 10 raised to 5 joule per mole. So we have to convert this. One photon energy is 6.626. Then 1 mole of photon energy. So what is the energy of 1 mole of photon? So for 1 mole of photon, energy, 1 mole of photon energy is equals to, so what we have to write here, 6.626 into 10 raised to minus 19 into 1 mole means how many numbers? 1 mole is equals to 6.022 into 10 raised to 23. I put the values here, 6.022 into 10 raised to 23. Then what will be the answer we got here? 6.626 into 6.022 is equals to 3.99 10 raised to minus 19 and 10 raised to 23. Then what will be the answer? 10 raised to 5 joules. So this is the 1 mole photon having the total energy. What we need here, just observe, what is the minimum energy needed to remove a 1 electron? They give us a kinetic energy. In the total energy, we are having work function and kinetic energy. We are having the two types of energy. Total energy is equals to work function and kinetic energy. Here what we have to need, the minimum energy need to be remove an electron. They give us a kinetic energy. Sorry, it is a plus. They give us a kinetic energy. So see here, the total energy minus kinetic energy. We have to do here the total energy and minus kinetic energy. Then we got the minimum energy needed to remove an electron. It's simple. Just minimum energy. We have to need here minimum energy is equals to 3.99 into 10 raised to 5 minus how much the kinetic energy they given to us, 1.68 into 10 raised to 5 joule per mole. 5 joule per mole. So see here, what will be the answer? We got the answer 3.99 minus 1.68 is equals to 2.31. 10 raised to 5, 10 raised to 5. I wish to take a common here. 10 raised to 5 joule per mole. 10 raised to 5 joule per mole. So see here, this is the energy, this is the minimum energy to remove an electron per mole. So what we have to find here, the minimum energy to remove an electron per mole. But we want for 1 photon how much energy we have to need here for 1 mole. That's why I wish to divide. So I wish to do this problem. See here, I wish to divide 2.31 into 10 raised to 5 joule per mole divided by mole number 6.022 into 10 raised to 23. Then what will be the answer here? 3.84 into 10 raised to minus 19 joule, because 10 raised to 23 when it goes here, it inverse 10 raised to 23 minus 5 is equals to 10 raised to minus 19, 3.84. So this is the minimum energy we have to required, or we have to remove an electron from the sodium. Then what they are asked? Maximum wavelength that will be caused a photoelectron to be emitted. So what we have to write here, already you know this, the formula E is equals to hc by lambda. What they asked to us? Lambda. So what we have to write here, lambda is equals to hc divided by E. What the energy we have to, what required energy to remove the minimum energy needed to remove an electron. So what we required here, minimum energy needed to remove an electron. So already we have find the value of the minimum energy for 1 photon. So I put this energy value here. H means Planck's constant 6.626 into 10 raised to minus 34 joule second into C means speed of light 3 into 10 raised to 8 meter per second divided by the minimum energy needed to remove an electron from the sodium, that is 3.84 into 10 raised to minus 19. Then what will be the answer we have to given here? 517. into 10 raised to minus 9 meter. I write as 517 nanometer. This wavelength is corresponds to a green light. This wavelength is corresponds to the green light. So this is the maximum wavelength that will cause a photoelectron to be emitted. I hope you got the clearance step about this problem. So once again I wish to repeat here. When the electromagnetic radiation of a wavelength 300 nanometer falls on the surface of the sodium, electrons are emitted with a kinetic energy, that is the 1.68 into 10 raised to 5 joule per mole. What is the minimum energy needed to remove an electron? What they are asked to us, the minimum energy needed to remove an electron from the sodium. They give us a kinetic energy, but they don't give the minimum energy to eject the electron from the sodium metal. We have to find that energy here, and what they are asked, what is the maximum wavelength that will cause a photoelectron to be emitted. So see here in the first step, we have to find here, or we find here the energy of, total energy of one photon, by the help of this wavelength, that is about 6.626 into 10 raised to minus 19 joule. So this is for one photon. We have to convert for 1 mole. 1 mole energy is equals to, then what happens, 6.626 into multiply by 1 mole of number, that is 6.022 into 10 raised to 23. Then what we get here, 1 mole of photon energy, the energy of 1 mole of photon. Then this energy, by the help of the 1 mole of photon minus kinetic energy, then what we have to got here, the minimum energy needed to remove an electron for 1 mole. What we got here, the minimum energy needed to remove an electron for 1 mole, but for 1 photon, so again we have to divide this by the mole number, 2.31 into 10 raised to 5 joule per mole, 6.022 into 10 raised to 23. Then we got for 1 photon, to eject the 1 electron or to remove the 1 electron from the sodium surface. So how much energy is needed? This much of energy is needed, 3.84 into 10 raised to minus 19 joules energy will be needed to remove an electron from the sodium surface. Then what we have to find next here, the maximum wavelength, and applying same formula in the place of energy we have to put this value. Then we got a 1 wavelength, that is 517 into 10 raised to minus 9 meter, and I write as 517 nanometer, and this corresponds to, or this is belongs to a green light. So this is our solution.